But then of course there is a problem here. If I have really a fundamental theory, those type of explanation in terms of mechanism, are not going to be available to us. There is no substructure that we can go and look for mechanism. So the picture that comes out of this is that we can think that there is some type of, let's say, metaphysical reality, but our physical reality, the one that is accessible through experimentation and that is describable by the law of physics, is really a subset. And then the physical theory are an idealized account of physical reality that make the system describable in a more convenient way. And so the issue here is that if you think about it, in physics we don't care about what can be formally defined, and we don't really care what can be computed, because again we care about what can be experimentally identified, what can be found and defined through a set of verifiable statements. And so not only there is more than one correct way to do mathematics, it's not necessarily true that the one the physicists are interested in is one of these that mathematicians care about. This video is based on a public talk that Professor Adala and I gave at the Advanced Studies Gateway at the Facility for Rare Isotope Beams, FRIB. There is a version of that talk online, and I put it there in the description. This is a sort of a more formatted and edited version, but the context is essentially the same. So we're going to be talking about several misconceptions in the foundations of physics. These are essentially ideas that were developed while working on our Assumptions of Physics project that aims to identify a handful of physical starting points from which the basic law can be rigorously derived. So it's a project on the foundation of physics, but touches also elements of the foundations of mathematics and those elements of philosophy of science that sort of help us understand what are these foundational issues. Through those projects, we're trying to sort of reverse engineer the physics law and finding these principles. We found that there are some, let's say, common held beliefs that we realized that are actually problematic, and that's why we call them misconceptions. And so this talk is essentially going through these seven ideas. So when people hear foundations of physics, a lot of the time they think of quantum mechanics and the idea that in order to understand quantum mechanics, you really need the right interpretation. And so what do we mean by interpretation? Well, one of the problems that we have in quantum mechanics is that it gives two laws of evolutions, two ways that a system can evolve. One is for physical processes, and this is the time evolution, the Schrödinger equation, the unitary operator, and the characteristic is that you give it an initial state, and the time evolution will always give us one and only one final state. And so this is the type of equation that we use when we need to describe the motion of particles, the evolution of fields, how fields and particles interact, and all that. Now then there is another law that is used instead during measurement, which is called also the Born rule or the projection postulate. And the idea is that you have an incoming state, you measure a quantity, and then you have a possible outcome for all the possible value that the quantity can take, and there's going to be a probability associated with each of the outcomes. So the law here is deterministic and reversible, and here instead the law is not deterministic. It gives us as output the probability distribution. And so the idea here is that at the end of the day, a measurement is a physical process, and so at the end of the day, at a lower level, it should be described by a process, and therefore the time evolution on the right. And the problem is that you can't do it. You can't take something that is deterministic and turn it into something that is non-deterministic. And so this is sort of one of the open problems in quantum mechanics. How does this process work? When does a measurement actually happen? What is a measurement? And so on. And so the general idea, what people generally think, is that you need an interpretation, something that tells you exactly what's happening during this measurement in terms of some time evolution operator, something that gives you a better idea of what's really going on behind the scene. And The problem with this view is that quantum mechanics is not only applicable for a fundamental particle like an electron, but it's also applicable, let's say, for a proton, which is not a fundamental particle, is made by quarks and gluon. But the proton, in many circumstances, unless you're really probing the internal structure, can be modeled as a single structure, as it were an electron with a different mass and a different charge. In the same way, an atom in many circumstances can be treated as a single quantum system, and even a whole molecule can be treated as a single quantum system. And for all these systems, you can have similar description in terms of diffraction and interference. All those effects are essentially going to be predicted by the same equation, and even during the measurement, you are going to use the same type of rule, the same type of projection. So the rules of quantum mechanics are not really applicable to only the fundamental elements, but to elements at different scale. And so if our idea is that, well, to really understand quantum mechanics, we really need to get this interpretation that tells you what actually is really going on, well, that description will inherently be different for all these different cases. And in fact, it opens a bigger puzzle. Why is it that all these different systems at different level of scale can be described by exactly the same equations? And if we really need to understand quantum mechanics, we would need an account for that. And it's unlikely that that's really one true mechanism that actually tells us everything, right? So the idea is that it's very unlikely that a single mechanism from a single interpretation can really tell us everything that's going on everywhere. So this is a very simple argument. It's an argument that I also pose to some people that work on interpretation, that do philosophy of quantum mechanics. So they recognize a problem, but then they say, well, but I'm really interested in fundamental objects, and so I'm only concerned with that. So why is it that there is so much focus on this type of this idea of interpretation, and why this problem is not generally recognized? Well, because there is another thing in physics that is generally assumed, that explanation must be about mechanism, because that's essentially what's worked for physics in a lot of areas, right? So we have a description at a very high level in terms of, for example, fluids like continuous matter, right? And then we realize that actually is sort of some sort of approximation, and then you get a better idea of what these fluids are made of when, for example, you look at the molecular dynamics and how, for example, molecule of water interacts with each other. And so you can explain sort of the macroscopic phenomena based on the rules of how these molecules interact with each other. And of course, the molecules themselves, if you really want to get a better picture of why that molecule has those particular properties, what are the type of bonds that the molecules can have, then you go and study atoms, and then atoms you study fundamental particles, electrons, and the nucleus, and you go until you reach quantum mechanics and get sort of a more explanation of why these elements work the way they are. So that there is basically this idea of a hierarchy of explanation, and the better explanation are the ones that are about constituents. So the physics really explain the behavior of physical systems in terms of the behavior of the constituents, and you go and go. But then of course there is a problem here, is that if I have really a fundamental theory, and I really have the fundamental objects, well, the objects cannot be further decomposed. So those type of explanation in terms of mechanism, are not going to be available to us, because by definition in a fundamental theory there is no substructure that we can go and look for mechanism. So if that's not the case, like what other types of explanation could we look for? Well, the idea is to look at the definition instead of mechanism. Let's just really think about what are the things that we want, how they are defined, and see if the definition themselves provide an explanation. So a process has to be something. What are the most basic thing that we have to require of a process to make sense? Well, In general, a process, whether it's deterministic or non-deterministic, will take a statistical ensemble, some type of probability distribution over something, and will map to a final ensemble, a final distribution. So we can understand the process as simply a map between initial ensembles and final ensembles. Now, one property that statistical ensembles have is that they can be mixed. We can take a source of one ensemble and a source of another ensemble, and then decide which ensembles to use based on a probability. So 50% of the time we use this, and 50% of the time we use that. And so this mixing produces another ensemble that is essentially a linear combination. It's a combination of the ensembles that we started with. And now there is a requirement between processes and mixture, because the output of a mixture must be equal to the mixture of the output. So whether we do the mixing at the beginning or we do the mixing after the process, we must have the same result. And so the idea is that processes must be a linear operation in probability of these mixtures. Now, okay, so this is for all possible processes, and now we can distinguish two types of processes. One is that there is deterministic and reversible, meaning that we can always find an inverse. We can find an inverse process that takes the output and gives us back the input. Now, under this assumption, what you are going to have when you conserve probability and you allow an inverse, you are going to get mathematically a unitary operator. So the fact that a deterministic and reversible process is described by a unitary operator is just a property of deterministic and reversible processes. There is, by definition, these things must have this property, and therefore mathematically they must be described with this type of definition. Now, if we have a measurement, we're gonna have a different type of requirement. So we want measurements to be repeatable. That is, if we measure in very fast succession the same thing twice, it must be that we measure the same thing. We have the same output both of the time. So it means that the output of a measurement, if we put back into the same measurement process, must give us back the same result. And so the idea that processes must be repeatable means mathematically that these processes must be idempotent. If you use them twice, it's the same thing. And a linear idempotent operator in mathematics is exactly a projection. So the idea is that the explanation as to why measurements are projection is really because these are the characteristics that we are requiring for a process that gives us a measurement. So the difference in behavior between deterministic and reversible processes and measurement is intrinsic to their definition. And any process that approximately satisfies these requirements will do, right? We never really have deterministic, fully deterministic and reversible process, because no system is completely isolated, and so there is always going to be some noise put in the system, and so the process is not really reversible 100%. In the same thing with a measurement, we're always going to have some tolerance. It's not going to be 100% repeatable in that fashion. But again, these are idealization of things that we want, and of course this idealization must have these properties. So it's not that there exist in nature things that are deterministic and reversible things and measurement. In nature there are processes, and then we pick these processes that with those characteristics, and we call them time evolution, we call them measurement, because they fit the definition that we are looking for. So again, you see the inversion here. We are not trying to find explanation from the bottom, but we are looking for explanation from the requirement, from what we are looking for, and these are the types of things that we are looking for, and we divide them and catalog, and that's why we have this definition. So again, there's nothing really so complicated about this approach. So this brings the question, why aren't these explanations more prominent in the foundation of physics? Well, again, there is a general sense in physics that the laws of physics are really the laws of the universe. So they are really there to tell us to understand what are the ultimate constituents of the universe and how they behave. And so the mathematical objects really represents real entity in the real world. And before, if you paid close attention, you saw that I implicitly assumed that physics produce a practical model of what is empirically accessible. We have these things, we have these processes has these characteristics, and then we can idealize in this way. And so the objects that are really in the theory are these idealizations. They are these things that we find useful to construct model and to explain things. They're not really a full representation of entities in the real world. They're only the things that we can measure and we can look at. And so is there a way to sort of look whether this is just a different idea, or there is actually some more evidence inside the physical theory themselves that that these are actually only about the empirical accessible part under some idealization. So what we have in our project is something called physical mathematics, with the idea that we start really from scratch and layer in each assumption to construct the physical theory. And the sort of the most basic object that we have, it's basically sort of an extension of logic, such that the logic that we have can keep track of experimental verifiability. So we have a notion of a verifiable statement, which is an assertion that can be experimentally verified in finite time. So for example, the idea that the mass of the photon is less than 10 to the minus 13 electron volt, that's something that we can verify in finite time, because there is an interval of uncertainty, and we do our measurements on, and at some point we say, okay, we will confirm this statement is really true. Now, something like the mass of the photon is exactly zero, this is not verifiable because of the infinite precision. We're never going to be able to measure a quantity with infinite precision such that we know exactly infinitely many digits about the quantity. And so what we do is look at a theory and say that, well, not all the statements are going to be verifiable, and there's going to be a subset of statements that are verifiable, and these statements that are verifiable are going to have an experimental test, and the test is going to succeed if and only if the statement is true. And then we look at the logic of these statements, and you realize that this is not the standard, you can't do the standard logic operation that you would do on normal statements. So for example, if we were to do the negation, the problem of doing the negation is that the test is not guaranteed to terminate if the statement is false. So if you now switch the false to true, now you do have a test, but the test is not guaranteed to terminate in finite time every time that the statement is true. So you do not have negation in general for a verifiable statement. What happens is that you have the finite conjunction, the finite logical end. If you have some statements and you want to test whether the end of all that statement is true, then you can just test each statement with each test, and if all the tests are successful in finite time, then you have tested the full statement. And so by looking at these properties of the logic, you find that the logic of verifiable statements recovers fundamental mathematical structures such as topologies and sigma algebra, and these are the structure that all the rest of the mathematics that we use in physics is built upon. And so the idea is that those structures that seem very abstract and seems also irrelevant from a physical perspective, are actually very relevant because they're there to keep track in our physical theory of which statements are verifiable and which statements are not verifiable. And so what we find is that these fundamental mathematical structure capture experimental verifiability. We also can go further than that. We can show that the use of real valued quantity is equivalent to a set of highly idealized assumptions on experimental verifiable statements. So the idea that time or space are a continuum is built upon assumption that you can always make measurements that are finer and finer and finer and finer, right? And this is an idealization. We know that that's not true. We know that at some point that has to break down. So the picture that comes out of this is that we can think that there is some type of, let's say, metaphysical reality of the things that really exist, right, that are there independently of us that exist. But our physical reality, the one that is accessible through experimentation and that is describable by the law of physics, is really a subset because it's only the things that can be reached through this verifiable statement, the experimental verification. And we saw that we can do fewer things with verifiable statements than we can do with the rest. So by necessity, this is a smaller set. And then the physical theory are an idealized account of physical reality. We have a step here of idealization where we put other assumptions that make the theory describable and the system describable in a more convenient way. And so these elements, right, the physical theory are actually here, they're not here. And so the idea that that the physical theories are modeled based on idealized verifiable statement, this is in our mind the correct viewpoints because it's fruitful, because it allows us to recover the correct mathematical structure, right? So it's not some kind of oh, I like it like that. No, it's a productive way to see it. It actually, I can do something with that perspective. I can actually get the correct math. And so the most basic mathematical structure can be derived through simple reasoning about empirical models, right? This is what we've seen in our research. And all of this could have developed and understood 100 years ago because in the foundation of mathematics and in the foundation of computer science, people were already aware and thinking about these type of things. It's just that computer science wasn't thinking about what is experimentally accessible. It was thinking what was computable, and in mathematics instead it was just thinking of what are the possible formal systems that we can well define. So why physics haven't looked at these things, and why don't we have something like this already well structured as the other disciplines do? Well, this again, I think it's really due to another point of view that is very common in the physics community, is that the laws of physics are found experimentally, not by reasoning. And this is something that I've seen and I talk to people that are very, very adamant about this. Because the idea is that the laws of physics are found by doing experimentation, not by reasoning. And so the idea that we can sit and think and determine scientific truth is really preposterous to a lot of people. And one of the examples that's brought up is that Galileo found out that objects fall at the same rate through experimentation, by dropping things from the Tower of Pisa, not by sitting there and reasoning. Okay, and so is that true? Is it something that we had to make an experiment for that, and there is no way that we could have reasoned that objects fall at the same rate? Well, so here is a way that you might have done it. So you can suppose that heavier objects fall faster than the lighter one. So this is the heavy object and this is the lighter one, and this will go faster than this. Now suppose that we connect the heavier object with the lighter object. We put them together, we put a rope around them so that they are forced to move at the same velocity, because either the rope breaks or these things have to fall at the same velocity. Now you have the small objects and the big objects, and the small objects want to fall at a slower rate, and the heavier object wants to fall at a faster rate. So the idea is that there is this rope in between, there is this mechanism to put them together, and so what we will expect is that the lighter object will slow down the heavier object, and the heavier object will bring and make the lighter object go faster. And so from this argument, we are basically going to conclude that the velocity, right, of the combined object must be somewhere in between. Like it can't be faster than the heavier, it can't be slower than the lighter. However, if you look now at the combined object as a whole is heavier than the heavier part. So if we said that heavier objects fall faster than the lighter objects, then we should conclude that the whole thing combined is a heavier object and should even go faster than the heavier object. But this essentially leads to a contradiction, right? Now we have two answers and they can't both be true because they're different. Now, if you assume that they all fall at the same rate, instead you put them together, they still fall at the same rate. You have absolutely no problem. And so heavier objects cannot fall faster than lighter one, because otherwise you have this contradiction, and we reach a stronger conclusion by reasoning, by arguing for it, because we know that there can't be a possible world in which things can be different. There's really not a choice, because the opposite choice really does not make sense. So we could reason, and by using reason we actually get a better insight. And the truth is that this is exactly what Galileo argued. This is the dialogues that he wrote in Italian, the original Italian. This is a translation. And he ends this paragraph by saying, you see then how from supposing that the heavier objects moves faster than the lighter, I can conclude that the heavier moves more slowly. Right? So Galileo did use reasoning, because Galileo, came from an Aristotelian philosophical tradition, of scholastic tradition of philosophy. So he knew how to argue. And so it may be then that this idea that we have always to find things experimentally and not by reasoning actually may be preventing us to finding things that can be better understood in the same way that we can do for the falling object. So can we find other lines of reasoning to justify other physical ideas? And this is exactly what we have found in our project, that if you look closely, you can find a lot of these things. So for example, in classical mechanics, states are defined by position and conjugate momentum, right? And so you ask why? Why is it that this is the case? Could it have been in a different, because it couldn't have been different, could have been the state only defined by position and not, and that's it. And what you find is that in statistical mechanics, you find that the count of configuration is given by these areas of position and conjugate momentum. So if you have an interval of position of 1 meter and an interval of momentum of 1 joule seconds times inverse meter, you have a unit, this unit of states, and this is essentially counts how many states are there for all the possible configuration. And now, if you look at the units, something that mathematicians don't really look at because they throw away, but a lot of physics in the units. If you look at the units of conjugate momentum is expressed is inverse units of position. So it's joules per second times inverse units of position, which in this case is meter. And so the product, you see, if you take this quantity and you multiply with this quantity, the meters go away, and the product it remains something that is independent of what units I used for position. So if I changed units and I went from meters to centimeters, then centimeters would increase. We'll have 100 centimeter, and the inverse centimeters, this quantity would go down because the units is changed, but the product between the two is the same. So the count of states becomes independent of what units we use for the position variable. And this makes sense because it shouldn't, right? So the number of states, the number of configuration of a system shouldn't depend on which units we chose to label the variables that we use to describe the state. And so now you can ask the inverse, right? Suppose that we require the count of states to be invariant because we want it to be invariant because that's what makes sense. Well, you find that the only way to do it, the only way to have an invariant count of states is that the state must be described by conjugate pairs like position and conjugate momentum. So the classical states must be defined by position and conjugate momentum, not because experimentally that's what we found, but because this is the only way that we can define state count, entropy, probability density, and even deterministic and reversibility, and also information in a way that is objective. And all these requirements, the fact that any of these is frame independent, that it's the same for all, is actually the same requirement. If you want entropy to be invariant, then information entropy has to be invariant, then density has to be invariant, and so on. And so if you look at the math closely with sort of a physics eye, we can find more conceptual reason for a lot of physics. And again, why is this not done more? Because there is nothing in these arguments that we're finding that are so complicated. This is something that, again, probably 100 years ago, 150 for this, somebody could have already made this argument. It's not complicated. So why is it? What is it blocking us from finding more of these arguments and give us more insight into the foundation? Well, one of the things that I think it's the problem is that again there is a sense in physics that the mathematical details are things for mathematicians to worry about. And we saw that some of these things, like the topology for the logic of experimental verifiability and these invariance that is due to the mathematical symplectic structure, right? These are things that you need to look at the math closely, you need to think about, and a lot of physicists says, yeah, that's just mathematics, because mathematics is full of technicalities that are uninteresting to the physicist, and it's job of the mathematician to find the correct formal framework and fix these details so that the physicist can worry about the physics. And again, this is kind of reasonable to have, because this is exactly what happens for all the other subjects. When you're making an experiment, you're not going to worry about all the details. A lot of them are going to be left to the mechanical engineer, the electronics engineer, the software engineer, which will fix these experimental setup and might give you a suggestion on what to use, right? So if you're using a TCP/IP stack over the network, this has absolutely no consequence on the type of experiment that you're doing and how you're taking the data and putting it on disk. This is just a detail that the engineer is going to be able to look at better and whatever. It's not that important for the physics. And so it sort of makes sense to look at mathematics and say, well, it's the same things. These are just details, and there's going to be a professional. It's up to him to look at these things. But the issue is that mathematics is not just a tool for calculation. It is the language used to formalize our physical model. And so it's there, the definitions are there to capture something about the physics that we're going to describe. And how can a mathematician who is typically not trained in physics know what are the correct features of the physical models? What are the correct definition and what are the correct tools to be able to capture correctly the physics that we need to describe? So for example, in quantum mechanics, we have a notional state, and the notional state is captured mathematically by an array in a Hilbert space, which is some mathematical structure that mathematicians came up with. And we have observable things that we can go measure, like position, momentum, and energy, and so on. And this is in the framework characterized, modeled by an Hermitian operator, which is again another mathematical structure that mathematicians have defined. Now, in math, there is a theorem that tells us that unbounded operator cannot be defined on the whole Hilbert space. And this is just a theorem that has been known for, I don't know, 80, 100 years, I don't know, a long time. And but what does this mean physically? Well, this means physically that for any Hilbert state, as long as it's infinite dimensional, there exists some state for which some quantity, like position, momentum, energy, number of particles, is infinite or not well defined. So if we have a state, psi, here, and we take position or energy, and we do the expectation of that, the average of that quantity, we get something that's infinite. Or it's not infinite, it's even worse, it's not even well defined. And of course, this is physically untenable, because what does it make sense for a state to have infinite energy, or for the average position of a system to not be well defined? What does it mean? It's not there. It's a physical problem. Mathematically, it's not a problem, because it's just a mathematical object, it follows some rules, and everything is perfectly fine. The problem is that it doesn't match to some physical system that actually makes sense. And so the mathematical details are actually physically important. It's something that we should look at, because mathematicians are not going to be able to know whether the space that they give us is the correct one for studying a system. So if we have the real numbers and we want to describe a mass, well, all the negative numbers are not going to be useful to describe a mass, because the mass cannot be negative. And it's our job to know that a mass cannot be negative. It's not the job of the mathematician. So we should have part of the physics community specifically working on developing physically and mathematically sound tools, things that satisfy the rigor, the modern standards of rigor of mathematics, but also that give us tools that are physically appropriate for the things that we do. I mean, we have something like that for sort of in the experimental realm to define units and to define scales of measurement, right? We have part of the physics community, a very specialized part, that worries about the definition of time, definition of space, definition of units constant, and all of that, right? And the rest of the physics community uses the output of this sub-community to then create the rest of the physics that we know and love. We should have something like that for the mathematical tool as well, but we don't. And again, why is it that we don't? Because this is something very reasonable to think that we should have. So we can't possibly be the first people that we discover this, but there must be something that is preventing us from going this path. And what is this? And we believe, because again, in the physics community, there is this sense that there is only one way to do mathematics, like there is the correct way, and it's up to the mathematician to tell us which is the correct way. So in the same way that there are the correct laws of physics, that you go and find them, there is correct mathematics, and mathematicians are there to discover the correct structure, organize them, so that they will be able to take our prototype theory, whatever mess of things that we create in physics, and give us the correct structure, because there is only one correct structure. And this is a problem, because in reality mathematics does not work that way. Mathematics is based on axiom and definition that are chosen based on the specific goals, typically the goal of mathematicians, because they are the one choosing the action. So a little bit of ironically, one of these axioms is called the axiom of choice, because it assumes that it is possible, if you have an infinite collection of sets, to be able to create another set where you take one element from each set. And again, this has puzzled mathematicians for some time, because one would think that you are always going to be able to construct this. Instead, no, you need an axiom to specifically tell you that you can do that. And you can accept that action, or you can reject that axiom. If you accept that axiom, then you're basically assuming that, that you're studying what can be formally defined. And what you're going to find is that this leads to the existence of objects that cannot actually be written down, that do not have examples. So for example, there is something called the well-ordering of the reals, and it's basically taking all the real numbers and ordering in such a way that each element has a next element, right? And there is a tricky way to do this, at least that it's definitionally sound, but one can prove that we are never going to be able to give you an example, because an example would require a string of characters that is infinite, therefore we are never going to be able to write down an example. And some mathematician finds that this is completely preposterous, because then we're talking about things that don't exist, and they reject the axiom of choice because they're interested in what can be computed, what can be actually instantiated and defined. And so the problem with this approach is that if you take this, then it leads to the non-existence of objects that are useful in physics. For example, the real numbers, again, are some of these objects that cannot be defined if you don't have something like the axiom of choice, because again, they're a string, like the decimal expansion of the real numbers is an infinite sequence that have no rules, and so you can't really enumerate all possible real numbers. And so the issue here is that if you think about it, in physics we don't care about what can be formally defined, because a lot of things that can be formally defined are going to be useless as models for what actually is experimentally verifiable. And we don't really care what we can be computed, because again, we care about what can be experimentally identified, what can be found and defined through a set of verifiable statements. And so the idea is that not only there is more than one correct way to do mathematics, it's not necessarily true that the one that physicists are interested in is one of these that mathematicians care about. And so we saw that all these this misconception are sort of constructed one on top of the other. And there is another thing that is sort of generally held to be true in the foundations of physics, that now that we have seen all this misconception, we will see how it is problematic. Is that this idea that a theory of everything, a theory that defines the smallest constituent of the universe, that tells us all the forces and all the work, this is the right foundation of physics. This is what we should work on in the foundations of physics, and this is going to explain everything. And again, it's reasonable if you hold the previous view, because a theory of everything will tell us what happened during a measurement in terms of some mechanism describing the most fundamental objects of the universe. And since the correct theory is determined experimentally, we should just focus on building rough prototypes. We would like to rough ideas, because in the end the mathematical detail is irrelevant to the physics, and mathematicians will later find the correct formulation. And this is a problem, because we saw that there are 6 problematic things that we are implicitly assuming when we're saying that this is the right way, the right foundation for physics. So if a theory of everything is not the correct foundation of physics, it's not going to work, then what should the foundation of physics be about? Well, again, why don't we look at successful branches of knowledge that have a good foundation and see how they do it. In mathematics, the foundation of mathematics define the basic objects and the rules used to do mathematics. So they're basically mathematical logic and set theory. Mathematical logic is about the rules, and the set theory is the rules of the prime objects, and everything else in mathematics is a set with some additional structure that is also defined by sets. And so this, the foundation of mathematics, what they give us a formal framework from which you can actually look and try to understand what can be achieved by mathematics. So we have proof theory, and proof theory describe what proofs are and what can be proved or not proved and what problems are there. And this gives you limits on mathematics. For example, we have the Gödel theorems that tells us that every formal system that is complex enough to describe the natural number will contain statements that are not provable. So mathematicians, again, at the beginning, 100 years ago, they wanted a system of thought where all the statements that could be written, that could be either proven false or proven to be true. And this basically says, no, you can't do it. Mathematics does not work like that. You're going to have a problem. If you look at the foundations of computer science, well, that defined the basic rules used to perform computation. In the theory of computation, you define symbols and manipulation of symbols. In information theory, you define a notion of information and information entropy and how this propagates through computation. And again, this gives a formal framework for what can be achieved by a computer. So complexity theory tells you that not all algorithms are going to be equivalent. Some problems are harder than other problems, and it tells you exactly why. And again, this puts limits on computer science. For example, it can be proven that there is no general algorithm to determine whether any other program will terminate or not. At least if you look at our computing devices that are essentially equivalent to Turing machine. And so, if that's the case for mathematical and computer science, what would be reasonable to expect for a foundation of physics? Well, it would be to define the basic objects and rules used to characterize physical systems, and to give a formal framework for what can be achieved through experimentation and through a theory that describes things that are experimentally accessible. And maybe we are going to find that this is going to lead to some limits on what is possible to describe in a physical theory. Who knows? But at least follows the same pattern. So, as you see, then we have a very, very different approach to the foundations of physics. We saw that a very common approach is to find an ultimate theory, a theory of everything, where everything else is just an approximation of that theory. We don't do that. Another approach is, again, to construct interpretation, to sort of clarify and extend the model, to sort of give a more in-depth account of what happens in a theory, such as in quantum mechanics for measurements. And again, we don't do that. What we want to find is to find a minimal set of a physical assumption from which we can rederive the law. And the idea that there are going to be some general physical principles and requirements, some things that have to apply to all physical theories, like experimental verification. Every theory must be connected in a precise way to experimental verification. And this is going to give us some abstract mathematical framework which all the physical theory must fit. And then we are going to have specific assumption for specific system in specific conditions. And under some assumption, you're going to get classical mechanics. And under some other assumption, you're going to get quantum mechanics and so on. And how would that look like? Well, this is the rough idea that we have. Again, in the general theory, we are going to have a layer that has to take into account experimental verifiability. And again, this is what gives us, as I said before, these topologies as in algebra that are the foundation for differential geometry, measure theory, probability theory, information theory. All these structures are based on that. Then after that, we are going to have some other layer that we call information granularity that is going to be able to tell us that some statements have a bigger information content than other statements, and we think that all the geometrical level, all the probability ideas and information theory, it's all done in this layer. This layer, we still don't know how to do it because we don't think we have the correct mathematics actually to bring this about. And then on top of that, we would want to have another layer that basically groups these statements together and tells us what are states and what are processes, so that we have a template for what a generic state, what are the basic requirements that we need to take a system, assign a notional state system. If we had this done right, then this would give us the space of well-posed scientific theorem, right? Theories, so it would be a mathematical space, and then we can go to give to mathematician with correct, like good specification, and then the mathematician can go and look at that and find what type of things can one find there or not. And once we have that, when we can take specific assumptions, for example, we have an assumption called of infinitesimal reducibility. The idea that if we have a system, we can think of the system as made of parts and the parts made of parts and so on, and studying the whole system is equivalent to describing these infinitesimal pieces of the system. And we believe and we can show that under that assumption, you can recover the classical phase space, so the state space for classical mechanics. And instead, you could make a different assumption. You could say that the system is irreducible, that you can't study parts, you can't make these parts independent. So for example, if I have an electron, whenever I interact with the electron, I have to interact with the whole electron. I can't take a red marker and make a red dot on my electron and say, oh, I only want to scatter with that particular part so that I know what that particular part is doing. No, you can do that. And so on the assumption that that can be done, that you have an irreducible system, we believe that we can recover the structure of the state space of quantum mechanics. This is a little bit more tricky because, again, we don't think we have the right pieces of math. We can do that for classical mechanics a lot better than we can do it for quantum mechanics, but a lot of the ideas are very similar. And then these are assumptions on state, on the system, and we can make an assumption on the process. So if we assume that the process is deterministically reversible, that for each initial condition you have one and only one final condition that you can go back, then what you find is the Hamiltonian mechanics, which is a version of classical mechanics for the classical case, and you can find the unitary evolution, the Schrödinger equation for the quantum state space. So again, the idea is sort of to reorganize all of physics based on these more fundamental concepts with, again, more general math that helps us understand what is different and what is the same across theory, and give us an idea of what's going to happen when these assumptions fail, so that it's going to be much more easier to construct new theories, because we know exactly what is it that is failing and we need to understand exactly how to patch things up. So again, the whole point of this talk is that we can give physics a much more mathematically precise, conceptually consistent, and physically meaningful foundation if we overcome those misconceptions. Again, those were misconceptions that when we started the project we also had, and we saw that they were a problem because we were getting results by sort of pushing those things aside, and we do believe that now those are things that are sort of major block roads in our path toward a better and more structured foundation of physics. So thank you for your attention, and again, if you have questions, you can put them in the comment. You can also look at our website if you want to know more, or look at other videos in this channel. Thank you again.